Okay, nice. Hi everyone. Welcome back. Our next it is our is it to improve the content analysis as well as questions. We have including speakers. The first one is implicit European problems and informal access. Well presented.
Yeah. Hi everyone. So I am Neelotpal. So I am a postdoc at University of Manchester Digital Manufacturing Lab. So I'll be presenting our CAD paper called Implicit Neural Field-Based Process Planning for Multi-Axis Manufacturing, Direct Control over Collision Avoidance and Toolpath Geometry. So this was done along with my colleagues Tianyu, Tao, Yongxue, and my supervisor, Professor Charlie, at Digital Manufacturing Lab in the University of Manchester. Yeah, so let's start. So before I start, so just a brief introduction of what the multi-axis in the title means. So this is a type of manufacturing in which, so we have different sorts of manufacturing based on how the tool moves. So the first we term as 2.5 axis, in which the tool just moves in along the two translational axis and incrementally along one the third translational axis. So something like the conventional 3D printers are designed to move along 2.5 axis motion. Then we have 3 axis in which the tool can move continuously along 3 translational axis. The image shown here of the Delta printer is commercially built for 2.5 axis, but because it has large clearance at the near the nozzle, so we can kind of adopt it to 3 axis. And then we have multi axis in which like it's generally classified as more than 3 axis depending on what kind of manufacturing you're using, in which the tool can translate along 3 axis as well as rotate along two or more different axial directions. So just an illustration of how it may look like. So we have shown a robotic setup that can do more than 3 axis of motion for the tool. Again, so this is the axis here means the axis of the tool, not the setup itself, because the let's say the robotic setup shown here has more than 5 axis, so it is 8 axis robot, but the tool motion is itself like 5 axis. So why do we need multi-axis? So I'll be showing some examples from the case of additive manufacturing, but we can have similar benefits for the case of subtractive manufacturing as well. So a few years ago, this paper from SIGGRAPH, they showed that using multi-axis motion, we can remove support material for different cases of FDM, which is a type of 3D printing. But very recently, there have been more functional improvements in the application wise. So this paper showed that uh, we can increase the strength of the parts by adopting by moving into higher axis of motion, because we no longer then need to be like in a planar domain, so we can deposit material in a curved way. And this is especially important if we want to like put in more anisotropic materials or more functional materials like continuous carbon fiber, where we can align, this allows us to align the carbon fiber along the stress directions, because according like the properties of those material are quite anisotropic, so they have higher strength, higher better function along the axial directions and not so great along the other directions, so it helps us to align them along the stress field. But what are the challenges? Like conventional 3D printer, like when we do 2.5 axis motion, the tool always almost remains above the printed substrate, so which means that there is less chances of collision with the part itself. But when you move into like the higher non-planar motion, there are increased chances of collision. And when this paper was published, the current methods did not control the collision directly. And also, we have seen that there is a disconnect between the layer generation and the path generation itself. So there are two subsequent different processes. Uh, they are not optimized together. And also, the geometry of the structure itself is indirectly controlled. Let's say if the curvature is controlled through Laplacian, which is not a direct control over the curvature, and then the, most of the processes are mesh dependent. Then it depends on the quality of the mesh that we have, and also as a result are not very differentiable. So in our case, we propose to have an implicit field representation. And why we use implicit field representation is, like, there are many reasons. One is that we could evaluate the field at any point in uh, in a very short time without needing for any interpolation, and also we can easily compute derivatives. So for our case, we use a sinusoidally activated neural network to as an approximator for a function, so which is used to represent the fields that we have. So for each coordinate, we output a field value, scalar field value, and then because the function itself, like the network itself, is differentiable, and especially because we use sinusoidal activation, so it can be differentiated any number of times. So we can easily compute the derivatives at any point. So we can compute the first order derivative, special derivative, which is the gradient, the second order derivative, the Hessian. So the pipeline is, we start with a computational domain, which is also represented as a sign distance field. Then we compute two different fields, which are called the FL, the layer field, and FP, the path field. And we can compute the isosurfaces of those fields, the LL and LP. Then we can take an intersection. So the intersection of the two fields represent the path along which the, let's say, the carbon fiber or any path, like along which the tool moves. So we have the layers, the isosurfaces of the first field, and then the toolpath, which is the isosurfaces, like the intersection of both the isosurfaces. So the manufacturing or other constraints can be computed using the field values and their derivatives. And we define different loss functions, which I'll explain shortly. And then we can define a combined loss. And the objective of the whole pipeline is to minimize the loss. And once we reach a satisfiable value, we can use those functions to represent manufacturable fields with desired properties. So in our case, we have three different classes of loss functions: the regularization loss that controls the geometry of the layers and the path. We have the functional loss, which can control things like support free or layer or path direction alignments when we want to align, let's say, carbon fiber along stress field. And then we have the collision loss. And our collision loss is the direct collision loss, which I'll again show how it works. So how does a collision loss work? So let's say we are printing something, and then we have a layer which was already printed, which is C minus delta, the ISO number. The current layer is C, and then the future layer is C plus delta. If we place the tool at the current point, you can see two different points on the tool, Y2 and Y1. The Y2 lies on a future layer, which means that there is no material there yet, and there is no interference with the tool, and this is fine. But the point Y1 lies on a layer which has been already printed, which means that this is causing a collision with the tool itself. So we don't want that. So simply we can put a condition that any point on the tool should have a scalar value more than the scalar value at the tip of the tool. And because we have an implicit field representation, we can easily compute the field value at any point. Hence, once we assign this constraint, we can easily come out of the collision zone. And this can be easily posed as a loss function. And here, if you see the loss x both on the scalar field as well as on the normal, the orientation of the tool through the points. Next, I'll shortly explain how we control the geometry of different layers, because we can compute the derivatives easily because of our representation. We can compute the tangential directions, the normal of the fields, and as a result, we can also compute exact measures of curvatures and geodesic curvatures for a path. Here are two examples of how we control the layer curvature and the geodesic curvature of the path using loss functions. Similarly, using similar derivatives, we can impose functional requirements such as support free, where we impose a constraint on the orientation of the tool with respect to the surface normals of the part that we are printing. Or if we want, let's say our toolpath direction is T, and then we have an input field direction field D, and we want to align the toolpath along that direction. So we could simply say that the cross product of the two vectors should be 0 at every point, which means that they should be parallel. And then we can generate similar loss functions for that. Here I'll show an example of our application where we show how we print a fertility model with support and collision-free constraints. And this is the actual uh, printing result that we do. And this is directly out of our neural, like the optimization network. We do not do any post-processing to avoid collision. And as you will shortly see, uh, we can avoid collision directly without needing any post check, and we can be sure that it won't collide because we like the collision was directly included during the optimization framework. And just quickly compared to the previous methods, uh, our method generated collision-free layers without sacrificing any of the other functional requirements, whereas for the other works, like through indirect control of collision, if we want to remove collision, it sacrifices the functional requirement. Again, so when we generated the loss function, so we put a we showed in condition for the additive manufacturing task, but we can easily uh, make it convert it into a general collision remove avoidance constraint and apply it to other layer-based manufacturing processes like CNC milling or rough milling, for example. So here I show an example where the initial layers for rough milling lead to collision with the tool, but our using our constraint, general constraint, we can it automatically generates layers which are collision free. And here is an example. Again, this is directly out of the result without any post processing for collision checks. And the tool can go into the cavity without touching any of those boundaries. Yeah. So next, coming to the other stage where we come, so an application of how we can do tool layer path co-optimization. Here is an example of a S-shaped break structure, and we have a field which is conformal to the top and the bottom layers boundaries. So if we want to, if we use a like like what previous methods did, if we generate the layers first, we end up getting something like vertical planar layers, which match the tangent surface, which match the tangent of those direction field. And then later, if we want to generate toolpath on that, as what was done in a sequential process, we get a toolpath for the fibers. And as you can see here, although the fibers, the toolpaths match the direction field very nicely, but there is some amount of curvature. And so are curvature is generally okay in the paths? Yes, for some material, but for something like carbon fiber, this result shows that as we increase the curvature of the fiber deposition, the frequency of the error or the deformation in the fiber increases, which leads to sacrifice of the structural properties of the fibers. And also, it's very difficult to have high curvature during printing. It's quite not manufacturable. But in our current case, if we increase the weight of the curvature loss, we end up getting reducing the curvature, but as a result, we also sacrifice the directional alignment of the fibers. Differently, if we use our method for layer and path co-optimization, because the layer stage and the toolpath level stage can communicate, we end up getting results which leads to reduction in both curvature as well as better satisfaction of the uh, toolpath alignment. So here is an example of a real example of application of our toolpath based frame optimization. Here we have a bracket, we apply a load and we get the maximal principal stress directions, and our objective is to align those carbon fiber path along those directions, in the same time also optimize the layers. So here you can see both the layers and the tool paths. The black are the curves are the tool paths are optimized together. One of the benefits of our using an implicit method is that we can also add other functions, like here we saw an example of optimizing the setup together with the the toolpath and the layers itself. And again, here is an example of how we print the long continuous carbon fibers on the layer. And yeah, so we use the same robotic setup with two different depositions. So here we print the base material, and then the other nozzle prints the continuous carbon fiber. And compared to the other methods, uh, like the previous baseline method, which showed that it could achieve high strength, our method has less disconnected patches, more continuity, and also, as you can see from the graph here, the deviation in the angle with the input field is less. And as a result, when we did the test, we found that the red curve is our method, the blue is the baseline method of the high density carbon fiber deposition. So in spite of using 18% less carbon fiber, we had significantly higher stiffness and bit higher breaking force. And this shows clear fracture in the fibers. Um, Again, this means that the fibers were clearly aligned along the stress field. So we also did a test on different applications, direction and layer, direction alignment and collision free for the layers, support and collision free, and also milling, which showed the universal application of our pipeline. A step further, so I said that we use sinusoidally activated neural networks. So this is like the function of like functional representation of the network, where we have a sine activation with a frequency term. And this frequency term can be really used to control how much information the network can express. But uh, there has been a lot of work around this area, because this is also a kind of a problem, because controlling we don't really know how we don't really understand how the frequency term affects our different manufacturability or different representations. Um, so there has been like different works that worked on some sort of says taming the high frequency noises in the network. So in our case, we did a analytical study of how different frequencies affect different functional results of our output. And I'll not go into details. So this is like we figured out some good frequency terms directly from the shape of the size of the part itself. And then some other terms, like we said that we control the frequency, the curvature of the path, but we sometimes also need singularity in the paths. And near the singular zones, the measure of curvature is not great. So we use some sort of curvature filtering. Again, more details in our paper. And then uh, we also improve some of the loss function definitions, so that the convergence is more stable. So as a conclusion, we generated a universal implicit scalar field optimization framework that enables direct control for both layer and toolpath generation in different multi-axis manufacturing applications. So we also formulated a explicit collision avoidance for field-based optimization, and then we showed how different loss functions can be used for joint optimization between layers and toolpath, and clearly this has several benefits. One of them I showed. And then we went into a bit of analytical study of how the expression of those functions can be controlled to control singularities and the regularization for the field itself, so that we don't really have completely rely on the loss functions. We could inherently condition the network or the function itself to express some of the required structures. So moving a step forward, so some of the applications that we showed here uh, used robots or little bit expensive devices, but then we tried it on commercial, like cheap printers. So on the top we saw a Delta printer, and bottom we saw the quite popular bamboo printer. And despite having very less clearance and only slight three axis motion for those printers, on the graph we can see that compared to planar printing, it still leads to significant improvement, and there is huge potential if the manufacturers start providing a bit more clearance, and hopefully they will do in the future. And also in our current study, in the paper that I just explained, we did not include any simulation in the loop, but our method, being differentiable, can easily be combined with one of the recent works from from few of our colleagues, and this will lead to a whole complete pipeline of simulation in the loop, where we optimize both the design and the toolpaths together, along with everything like collision avoidance and all the manufacturability constraints. So, speaking about limitations, there are a lot. So, the first is we did not include support region during the optimization for collision. Then we did not include kinematics during our optimization, which is another scope. So, as a result, our tool had to be during the collision check had to be symmetric because we did not know how it would like align along the axial direction. Then our collision avoidance for the milling is too conservative, which leads to a bit of distortion in the path, which probably in the future we can solve. And then we only included a limited number of constraints in our current work, but then there is we can do a lot. Like we can include path length, tool path length, or path like layer areas during the optimization, which can be easily done because we have a implicit formulation and we can compute those values easily. Yeah, those are some of the limitations that we have. And like if you would like to know more, I can discuss after the session. Also, I have brought a few parts if you'd like to see how they actually look like, the printed parts, and I have a few more tested parts. And that's all from me. Thank you so much. And we have our code and all the results open source, so one of that. Thank you. Uh, there are multiple reasons. First is that the conventional printers print at like very low layered height because we wanted to test our parts. Like we had less time, so we increased the layer height to like several times. Like let's say the bamboo printers print at 0.2 millimeter height, we print at 0.6 millimeter height. Uh, we did not explicitly control the surface quality in our method, but I can show some of the results where we have better surface quality because we use less layer height. Second is 0.8 millimeter. And we do not we have not controlled the kinematics of the tool in this paper, which means that the robot motion is not smooth, which again can be optimized. And yeah, so these are a few of the answers. And uh, like there is scope. So also we did not control how the material dynamics. So we did not control the extrusion rate and all of those things because for this work it was not relevant. But we have done some current works where we could improve the surface quality and reach better. But that needs more work, I think. Yes, there has been some works from our like co-authors which are working towards uh, the trajectory optimization dynamics of the tool. Even Dr. Fang has recently published a paper where he optimizes the trajectory. I think it can be possible, and just because our pipeline is differentiable, we can easily make the whole kinematics kind of differentiable and put it as a modular setup where you can switch on and off different requirements. Uh, yeah, I think it can be done, and I do not see why it can't be. So
to be race, how you will be minimized in the race, makes sense. One way of
Possibly, yes, because I mean, reducing the degrees of freedom would possibly increase the ease of control, but also I think it would reduce the generality of like the applications. So if you have a certain structure of a certain manufacturing process that you just want your device to be applied for and certain class of parts, I think you can definitely optimize your device for those applications with for better results.
minutes, so let's send some signal again. Second, well, second, okay, the second speaker is Bahari. He will the additional small and students in the artists in isogeometric analysis or small and THB slides for grading non-linear problems. Yes.
Okay. Thank you for the introduction. So our paper is about simultaneous RH adaptive isogeometric analysis using THB-Splines. And well, we didn't have up to now an introduction to isogeometric analysis in this conference, and nor I will make one. But briefly speaking, we want to use B-splines and splines in general in numerical simulation. So we regard the spline spaces, the spline basis functions as functions for finite elements, say. And in this context, there is a lot of developments and a lot of technology in order to do local H refinement. So to locally enrich the mesh, like the mesh you see here on the left. So you have a tensor product mesh, a tensor product grid, like the one we use for representing a parametric surface with interior nodes. And we would like to have some locally inserted nodes in these areas in order to enrich the space locally in the middle while keeping coarse basis functions around. There are a few technologies to do this, such as the T-splines, LR splines, and hierarchical B-splines. And the hierarchical B-splines is the ones I will use in this talk, but I will not introduce them at all. Because what I want to do in this talk is to actually consider another type of refinement, which is called R refinement, coming from the word relocation refinement, where essentially in the terminology of CAD, it would be reparametrization. So we can reparameterize a surface, and so we can compose it with another map and have a new parametrization. This implies contracting, say, the isoparametric line, so you have new elements, new subdivision that concentrate, as you see here, in the middle. So this is the R refinement. This is a relocation of the nodes, because in our finite element analysis, these are just nodes that will be used for the numerical simulation. And what I want to do now is to combine the two. So take the best traits of the both and present you an approach that we can locally H refine and R refine the mesh and see what that gives to us. So schematically, you have the R refinement. As I said, you start with this square domain. You reparameterize, so you do the R refinement step, and you get concentration of the nodes around the regions that are implied by your monitoring function. This monitor function is a function that tells you where you need to concentrate your nodes. On the other side here, you have the edge refinement. So you start with the same grid, but then you locally enrich the grid and you keep the map F fixed. So you arrive in such a situation. And what I want to do is to combine the both. So you do R refinement and then edge refinement, and you arrive to a mesh which is locally refined, and also the nodes in the mesh are relocated, so they are not standing, they are not following the initial parameterization F. Okay, so that's the initial map in F. And this relocation refinement happens using this map, which is a Mont-Ampere mapping. We are going to use to solve it using solving an optimal transport problem. So we will compute an optimal transport in order to relocate the nodes, and then H-refine additionally to locally refine the mesh and iterate. So just briefly introducing the optimal transport problem. We are given two densities. The initial density is R0, is essentially the unit function, and you have a target density ρ1, which is the function which is the density that you want to have at your relocated mesh. And what you want to compute is actually this psi, which is this relocation map that takes you from ρ0 to ρ1 with minimal transport. That it means such that the cost of this map is counted by the amount of distance that each point traveled from your initial square to your final relocated position. And all this by maintaining the mass, so maintaining the integral of the density. So there is a well-established theory. We know that the result psi is actually a convex potential, and we know that to solve these equations, we arrive at this kind of equations where we have the determinant of the Jacobian and the Hessian multiplied by the density ρ1. So, long story short, I will skip several details, but finally what I want to arrive at is that this problem, finding this psi, reduces to solving this nonlinear Poisson problem. So you arrive at this Poisson equation where your convex potential phi is your unknown solution and its gradient is your relocation map. And in order to solve this, since it's a pure Neumann problem, you can use, it's a nonlinear problem, we can use Picard iterations. It's simpler than Newton method, but the non-linearity is not so strong here and it works actually quite well. And since you have a pure Neumann problem, you also might need a mixed formulation to solve it. And moreover, there is a third problem, which is that when you actually enforce the Neumann conditions weakly, you might get not 100% accuracy in the boundary, because the weak imposition of Neumann conditions is never exact. So we get these problems on the boundary, meaning that the map is not transported directly on the same square, but there is an error on the boundary. Okay, with this, I can tell you about our first contribution in the present paper, which is to propose a projection method to solve this Mont-Ampere equation. So instead of going to a mixed formulation, instead we project at every step of the Picard iteration. We project the gradient of the potential, and we obtain a new spline function that we can evaluate for the next step. So all this solution is happening in the isogeometric sense, meaning that we use B-splines to solve this equation. We use tensor product B-splines to solve it, and we obtain the solution as a function in a spline space again. Then, in order to tackle this problem with discrepancy on the boundary, as a last step, we would project back the boundary control points on the unit square on our original boundary in order to preserve the exact boundary. And if you do that, this is what you get. You get that your final result it's like we snap the control points back to the unit square, because that's always our domain. And in that case, we can recover the one-to-one mapping. And we could actually show with a small proof that when we do this boundary correction, the map remains safe by ejection. So we can still use this map to relocate the nodes without any problems in our Jacobian map. Okay. So we tried this approach and yes, I show you here some comparison. This is the error in the Monge-Ampere equation that you would get, and I'll show you some comparison between our approach, which is here, and the approach if you use a mixed formulation, which is what would you do in a classical finite element setting. And we can see that this is much more efficient because when you do this mixed formulation, you double the number of degrees of freedom, so you double the size of your problem. Okay, so then up to here we have the relocated map, we have our adaptive mesh, but we want to use this to solve actually some PDE equation. And here comes our second contribution, which is to test this new approach in some solution of PDEs. And when we do that, we have actually several possibilities. We could do an initial R refinement so that we relocate the mesh close to our features, say, and then continue with a number of H refinements. We could do a number of H refinements and finally relocate then the mesh as a last step, or we could iteratively, simultaneously do RH, and in the next iteration again RH, RH, meaning every time we relocate the nodes and we use some a posteriori error estimator to also point to H refinement. So we call these methods a priori reparametrization, simultaneous adaptive method, and a posteriori misalignment, so ARM, SUM, and AMA. And yes, here you can see some illustration of the two. So, okay, here you have pure R refinement, pure H refinement, and the combination of the two. What we can see that we gain the advantages of the R refinement. That means that our initial nodes are better following our monitoring function. And finally, by doing H refinement, we can concentrate even more at the area of interest. So by comparing all these different strategies to combine the two, we realized that the simultaneous RH refinement is the more suitable to do. And another ingredient in this process is where you do your what you use to solve your Monge-Ampere equation. What basis you use to solve your relocation problem. Since so and then with these examples, we actually wanted to keep the computational cost low. So we always solve the initial Monge-Ampere equation on a tensor product basis. We don't use the adaptive basis, the adaptive H refinement to relocate the nodes. When doing that, there's one advantage is that we can use fast diagonalization. So it means we can exploit the tensor product structure of the tensor product splines in order to reduce the computation time. So it's a known technique when you have a tensor product grid that you can actually solve this equation on the square with much less computation time than if you would use the full solver. Like here we compare with a conjugate gradient solver that uses n squared number of degrees of freedom, and fast diagonalization would reduce the problem to a number of n times n smaller problems. Anyways, long story short, the best thing is we obtain good results with fast diagonalization and conjugate gradient, but with respect to CPU time, the best is to use fast diagonalization for this step. And that's what you get as some resulting meshes. That's pure H refinement, that's one R and then two H refinements, and that's two successive RH cycles. Well, you don't see much of a difference in these meshes, but it's because I cannot really draw very fine meshes because you cannot see them anymore. But in general, what we have observed is that the RH, the SUM approach, or the simultaneous RH refinement, is what works the best because it at every step it can relocate and improve the mesh closer to the features of the density. So you see the density here dictates that we should concentrate the mesh along these swirl lines. Okay, and again, this is some meshes with simultaneous refinement. On the top, you have pure edge refinement, and on the bottom, you have edge refinement, but it is enriched with R refinement. In practice, what do we see? In this R refinement, what is important is that the mesh can be aligned to your features. No matter how far you might do edge refinement here, the parameterization cannot rotate, will not rotate, is fixed. So your elements will not rotate and they will not be aligned to your feature. Whereas here, when you allow to relocate the nodes, you see that there is some rotation happening and the alignment is much better. So that's why we believe that the combination of the two can bring the best of both worlds. So then we put everything together. One more ingredient is that we need to actually generate this monitoring function. And when you have an a posteriori error estimator, usually you have an error value for each element. So you know that the error is that or that in every element, but that's a discontinuous function. These are just sub-values. And the first thing we want to do is to actually generate a smooth monitoring function, because we need such a function for solving the optimal transport problem. So what we do is that we project these values on a grid. We project it using a projection operator, and we obtain a spline function that we can use in the sequence. So we smooth out the error, and this error, as you see here, is the PD operator minus the right-hand side, so it's the residual error, okay, on every element. Q is every element of our mesh. There you have another example. On the left, just pure edge refinement, and on the right, on this sphere, you also have mesh alignment together, RH adaptive refinement. And on that one, you can see that if you compare with uniform refinement, which is the blue, you compare with pure edge refinement with different refinement thresholds. And if you do just R refinement, which you would do on a tensor product grid, all of these become not as efficient as if you would do what we propose, the combined RH refinement. Here we could not do another step actually, because to do another global step, we would have to refine globally one more time the tensor product basis, and this would make the number of degrees of freedom to explode. Whereas here, you see that aligning the mesh with R and locally refined with H gives the best results. And with respect to H1 error, the picture is the same. Okay, and yes, one last example. Here we solve a advection diffusion equation. Here is with just locally refined THB-Splines. And you see that we get a nice solution, but in these sharp layers, you see that even though we put a lot of degrees of freedom, we don't arrive to completely eliminate this effect of the transition. Oops. But if we do an R refinement step, then we better align the mesh, and the sharp layers become much sharper with the same number of degrees of freedom. So we are much more satisfied with this than with the original solution. And another one is we applied this with to the elasticity benchmark on this quarter annulus. Again, the RH is the more efficient to do. And yes, you can see that if it was a pure H refinement, then you would get this kind of mesh. But if you do RH refinement, the original mesh concentrates close to the high stress areas, which is this part here. And then the H refinement refines in a different way, so to say. Okay, so to draw some conclusions, we tested this technology of RH refinement by combining node relocation and local refinement in order to get the best traits of both worlds. I would say the best trait of local H refinement is that you can locally refine the mesh at will where you want it. But the extra trait that is very interesting in relocation refinement is that you can align. You can align and you can reparameterize so that you capture much better features on your solution. And yes, another thing that we're investigating is how to how to make this technology compatible with the rest of CADs, so to say, because as you might have noticed, when we apply this RH refinement or this R refinement in general, our final object, our geometry, is not anymore a spline, but it's a composition of two splines. So in that case, this is not directly compatible with CAD systems, and we would have to find a good way to project back to the spline space or to export to something which is compatible. And so with this, I'd like to thank you for your attention.
Yes, very very interesting. Thank you, Angelos.
Thank you.
So, always first are
Not always. So our method of choice is to do successive RH at every cycle. Yes, first R and then H. Yeah. Mhm. We can do both. The reason why we do first R is because we want to stay with the tensor product basis as much as possible. And yes, first we only have the tensor product basis, and solving there is efficient. So that's why first we do the R.
And then if you have a part of these, then you don't use these sides.
We still use another line tensor product mesh because it's more efficient. Mm.
Yes. This makes also small civilization over. What's the main problem? Significantly consider move the mesh or what is the trigger?
Yeah,
Of course, it's very easy.
I see.
It's
Yeah. Yeah. Okay. So for getting the first of all, it is a method that is known in finite elements mostly. Recently in isogeometric analysis, pure AR refinement. I guess there is some extra layers. There is this density function that you need to approximate. There is this extra system to solve. Here we alleviate that because we go to the unit square. We solve the equation from unit square to the unit square. You can imagine in an unstructured mesh, you cannot play this trick. So you have to solve another PD before solving your PD to get the mesh. And what else? Maybe also, of course, there are always problems with bijection. Maybe in some cases you don't get bijectivity. Yeah, maybe there are all these things to consider. So to say, it's an advanced remeshing method. So it comes with all the problems of that, for sure. Thank you.
These stopping is also very good. Very well, it's in part. Depends on
Times makes sense.
Yeah.
Yeah.
Yeah, yeah. Do it again. And do it again.
Yes, please.
This experiment is being installed. It's saying
Hello everyone, I'm Jingyi, a PhD student from Dalian University of Technology in China. My report is Extended and Adaptive IsoGeometric Analysis for weak-discontinuous problems. The co-operators on this paper are Yejie, Matthias, Möller, and Chungang. I will introduce it from the following four aspects. First, I want to introduce what the weak-discontinuous problems is. Weak discontinuity problems are a type of physical problem where the solution is continuous, but the derivative of the solution is not. There are many reasons for this kind of discontinuity. Compositions, layered structures, pore source, uneven interfaces are frequent in engineering and biomedicine. For example, in the figure, the store wrapper in concrete on the left and the tools and the surrounding bones issues on the right are common inclusion problems. This kind of discontinuity will affect the accuracy unless the discretization is adapted to the interface geometry. This is the interface boundary condition. To deal with the discontinuous here, a lot of methods have been proposed. Edge refinement, accurate but cumbersome for complex geometry. Extended finite element method, capture the jump but as degree of freedom. IsoGeometric analysis method, exact geometry, high smoothness, but that smoothness is run across a kink. Are adaptive alone in isogeometric analysis method. Relocates points, provides cascade, but can't reproduce the derivative jump. In isogeometric analysis, splines used to represent the physical domain are also used to construct the solution in the computational domain. However, only the control points located on the boundary affect whether the spline combination can accurately represent the physical domain. Therefore, we can remove mesh quality by moving the coordinates of internal control points. This approach doesn't change the mesh topology or add extra degree of freedom, and it allows the mesh to better adapt to key areas of the problem. Extended isogeometric analysis is a method which combines the geometric advantage of isogeometric analysis with the enrichment strategy of extended finite element method. But geometric resolution still misaligned with interfaces. So we proposed extended and adaptive isogeometric analysis. It's worth maintaining that our adaptive method account for less than 1% of the total computation time. The next part is our method and algorithms. Our method compiling enrichment with control points relocation. Enrichment provides the approximation space needed to represent the current jump. Our adaptive redistribute the existing resolution towards the interface. Finally, this accuracy improved by more than 16%, and the extra time it took was less than 1%. I want to first introduce some knowledge related to the extended isogeometric analysis. It's a strong form for linear elasticity with weak discontinuous. U represent the unknown displacement. Sigma is the strength tensor and B is the body force. This is the interface boundary conditions. These conditions indicate the discontinuity of the displacement garden at the interface. simplified to the weak form based on the principle of minimal potential energy, and on this basis, use extended isogeometric methods. Based on the partition of unit enrichment paragraphy, the extended isogeometric method adds enrichment functions to the interface-related parts to capture the spatial changes near the material interface. Only control points whose support interfaces are enriched cite n faces. The enrichment function phi is contributed from the level set functions, which is used to distribute the position of the material interface. When it equals to 0, it corresponds to the interface where the materials meet in the physical regions. This is the Maxwell ensemble process, and adding the extended part can fix the discontinuous of this kind of problem. When solving these problems, there are two types of the elements, standard elements and cut elements. For standard elements, a Gaussian integration with P71 multiplying Q71 points is used. For cut elements, if we still directly use standard Gaussian integration, the integration points may fall into different material regions at the same time, which would reduce the solution accuracy. So a stage of subdividing into smaller triangles is used, with 30 integration points for each subdividing triangle. The picture below shows from the integration points are distributed under the integration strategy. In the zoomed-in image in the right, the black triangles represent the sub-element divisions, and the red dots are the integration points. To check how the optimization method improves the accuracy of solving the problem, we use related energy error as the measurement standard. According to the error estimation method proposed by Sinkwicki and others, the small strange field value S is used instead of the real strange field epsilon to calculate the error. The whole computation process can be divided into three parts. First, in the physical space, we based on the KS allocation to use level set functions building a function. This function's value represents the proportional distribution of geometric redistributions weights in the physical domain. Then we use this function to build a Gaussian type multinomial function. The multinomial function is used to update the control points in the parametric space. Finally, the physical equations are solved based on the updated control points. This process has no knock insertion, no degree division, and the typology preserved. Then I want to introduce the specific process of constructing the multinomial function. The function constructed based on the KS allocation is as follows. Here, phi kx is the level set functions. Use phi x to construct the monitor function in the following format. Based on this function, we then constructed an electric optimal to solve the new control points. The method works for any number of methods. The multinomial function reached its maximal value, rho max equal rho 0 or multiplying alpha at the interface, and smoothly decreases to the background level rho 0 as the distance from the interface increases. So alpha rate rho 0 determines the magnitude of function's variations, while delta controls the distance of the multinomial function's influence. Based on our method, we construct the monitor functions and move the guide on the latter's SPM. Figures A to C shows the numerical distribution of the level set functions for 3. Figure D shows the maternal functions constructed using the KS aggregation method. Figure E shows the quality function, and the final grade moment effect is shown in Figure F. We use a PDE-based R-adaptive parametrization method. By solving the equation, we get new control points. This equation can be understood as the Euler-Lagrange equation of geometric functional, which rearranges the distribution of control points according to the numerical distribution turns to the maternal function. To keeping the geometric contribution, the control points on the boundary remains unchanged, and it can be eventually by simplified to solving the following equation. The whole process is a positive definite linear solve and doesn't depend on the initial solution. Also, the time span increases with the number of control points. The overall obtained process can still take up less than 1%. This part is the benchmarks and results. This is an example of a circular air with two materials. Figure A, C, D are the exact solution of displacement, the numerical solution, and the absolute error distribution. Figure B is the result of our adaptive parametrization. It can be seen that the degree of freedom tend to contribute at the boundaries. The left image shows the relative errors calculated and compared on the same set of degree of freedom for 4 methods. XFEM, XFEM combined with R-adaptive, XIGA and XIGA combined with R-adaptive. It can be seen that R-adaptive optimization can constantly improve the calculation accuracy, and the degree of freedom increase, the optimization account becomes even more noticeable. The right image shows a comprehension of computational costs, and the time used for optimization always counts for less than 1% of the total time. This is an example of 4 calcular interfaces. From this, we can see that the method can also improve accuracy when there are multiplying interfaces. This is examples for 3 calculator interfaces. Even though the interfaces are closely packed, our method can still optimize them eventually. This is an example of a heart-shaped interface. The tip of the heart is a special point that needs excitable attention. As can be seen from the figure below, the arrow is eventually introduced, while still ensuring computation efficiency. Finally is the conclusion and outlook. First, we proposed a copter enrichment and R-adaptive strategy within the IsoGeometric Analysis framework is developed for problems with weak-discontinuous. Secondly, a monitor function was constructed when greatly reduced errors while taking little time. Finally, various numerical examples show the effectiveness of this method. For future work, we plan to extend it to 3D problems and more example problems. Using this method for problems with strong discontinuous. Thinking about setting up a more automated optimization strategy. Thank you everyone for listening. Here is our method. Feel free to contact us if you have any questions.
Maybe I want to ask what okay, I'm not really expert in this field, but I will come explicitly all those injective constraints in your method, which means that the measurement of each other and it be controlled in your method.
Uh, you speak again?
Yeah. So because the compound was being modified, right?
Yeah.
Can you guarantee that the mesh will not fall in precision after the update?
Yeah, we can move them again for another.
So is this considered by any objectives?
Yeah.
Yes. Yes. Yeah, it's guaranteed experience. It's basically it's easy for because we saw a big and according to the Latin theory, it's guaranteed on the 20s. That's usually okay. Thank you. See by let's ask another one. Sorry. So for the extension of 3D, how challenging will
Maybe we do it now, and we will take a actual later, and maybe the extended part may be different, and the adaptive to 3D is, yeah, naturally.
okay. So maybe we can make that. Great. So if no more question, I send the speaker again. I thank you.